we are part of Extension, which means that we're doing research, we're doing outreach, we're doing education all at the same time. So as we learn more, we're supposed to go out and talk to people about what we know. What I know today is more than I knew 3 months ago. What I'll know next year will be more. So it's kind of a sliding scale. I got involved in oil and gas stuff in the 80s because we had injection well failures, and private water supplies were getting contaminated. And they were getting contaminated a whole lot faster than they were supposed to be, which really led to what my doctoral dissertation work was on, which is looking at essentially cracks in dirt. So cracks in rock is cracks in dirt on steroids. And I was placed on the commission, the governor's commission, because they needed somebody that knew something about groundwater, and they needed a girl. And I'll tell you, in the 1980s, girls who knew about groundwater were pretty thin on the ground. There were probably 3 of us in the state, and I worked with one of them. So, we held hearings all over the state. We changed the rules. We had good rules in the late 1980s, but guess what? That's 25 years ago, and we basically didn't do anything since that time. And things got real sleepy, and nobody did anything. And then about 2011, we started drilling shale wells. And it was just about this time 3 years ago that I said to some of my coworkers, Black Shale's radioactive. What are they going to do with the cuttings? Well, nobody really talked about that. So I spent a day on the phone talking to Ohio Department of Health, who sent me to Ohio EPA, who sent me to Ohio Department of Natural Resources, and round and round and round and round. And no one could tell me what they were going to do with the cuttings. And almost everybody I talked to didn't know they were radioactive. And I said, how can you not know they're radioactive? But they didn't, or at least they didn't admit to it. And so that got me started, because since I work with water supplies, I have to keep those water supplies clean. Because now we're starting to throw radioactive stuff around, and I got to worry about where it's going to go. So, there. Okay. Now, this may be strange to put on a slide, but I've learned I have to do this. I have to have a disclaimer. You're going to hear all kinds of things about oil and gas drilling. The first question you have to ask is, who are you hearing it from, and what is their background? If they are scientists, if they are engineers, if they are registered sanitarians, they pretty much have a ethics requirement, which means that they need to tell you what they know to be true. And if they tell you something that they know not to be true, you can complain to their registration or certification organization, and you can get their credentials yanked. So we have to be very careful what we say. However, public relations, politicians, and political appointments have no such bounds on their statements, and political spin is their bread and butter. And I throw that out because I've heard some pretty outrageous things said that I know are not true, but I can't call them down because they don't have any credentials to call them down on. So it's important to, when you hear something, find out who is saying it and where they got their information. Don't believe everything you hear. Now, black shale is radioactive. Well, why? How? Well, it's natural. And that's because we are stardust. And everything in the universe is stardust. We get hydrogen to boron with the first Big Bang. And then carbon and all the rest of the way down come from the supernovas. So all of that dust that comes together that became Earth included radioactive materials. And that's not a bad thing, because radioactive materials means that our plates move and means that our mountains build. And if we were not radioactive, we would be a cold, dead planet and we'd look like the moon, and that's not a lot of fun. So being radioactive is not a bad thing. It's just that you don't want this stuff in your backyard. Okay? And that's the really important part. So how are black shales radioactive? They're radioactive two ways. First of all, it comes from their parent material. Where did they come from? The black shales that we're talking about, the Utica and the Marcellus. The Marcellus comes from the Appalachian uplifts, the earlier ones, washing into the marine environment. The Utica is older. The Marcellus is roughly 300 million years, plus or minus. The Utica is another 150 million, plus or minus. It comes from the Canadian Shield as well as those earlier Appalachians. And so you've got parent material of radioactive materials coming in and being part of the source. But the big reason that the shales and the coals in Ohio are radioactive is because of something called bioaccumulation. Does anybody have a Brita water filter on their faucet at home, or know anybody that does? Okay. Water treatment plants have activated carbon filtration systems. Shale is an activated carbon filtration system, except that it's been working for 300 million years and nobody got around to cleaning the faucet and changing the filter. And so after 300 million years, it got pretty gicky, okay? Because as surface and groundwater move through carrying the heavy and radioactive metal cations, they're moving through this organic carbon, which is a really strong negative magnet. And it's throwing off the light stuff. It's throwing off the calcium. It's throwing off the magnesium. It's grabbing onto the strontium. It's grabbing onto the barium. It's grabbing onto all the heavy stuff and all the radioactive stuff. And the older the rock is, and the higher the carbon content, the more radiation, if everything else is equal. The higher the sources, the more radiation, everything else being equal. But this is a natural phenomena. It's just that it's a natural phenomena a mile down in the earth. Okay? Now, when I was talking to everybody 2011, they said, oh, we've never heard of this. Okay, so I did some backtracking. Here is a wonderful publication out of 1960, U.S. Geological Survey for the U.S. Atomic Energy Commission. I couldn't find anybody who didn't know shale wasn't radioactive. So I'm going back to see how far back we knew. So here's a 1960 publication all about it, okay? And we're finding that there are many, many other documents that are a whole lot older. The coals in Ohio and their ashes all got analyzed through the Department of Geosurvey and USGS's chem labs in 78, 81, 86, and 88. Those are publications you can get right now and read. They've got all of the coal-bearing townships, all of the coal seams, the chemistry of the coal, and the chemistry of the ash. The shales analysis are kind of scattered through a number of documents. The natural radon data was published in 1993 by Geosurvey as well. And here's one of the radioactive shale reports. This one is 1982. That's 32 years ago. This is not new information. And if you look at this cross-section, it comes through Stark and Columbiana County. And this little, if I'm going to hit the right button, no, above, here. Right there is the Marcellus Shale, bottom of the Devonians. And from here on up to the Berea sandstone is the Ohio Shale. I'm sitting on top of the Ohio Shale in Columbus. My house is on top of it. So 32 years ago, this was published. So this is not new information. And one of the things they were looking at was, where is it predominantly radioactive, and where is it normal radioactive, and where is it in between? So all of those black areas were already mapped in 82. And they mapped them off of Schlumberger logs. Okay. So, why does this matter? Well, it has to do with this definition of radioactivity and naturally occurring radioactive materials and technically enhanced naturally occurring radioactive materials. And there are actually 4 national definitions for the difference between the two. Ohio uses the Conference of Radiation Control Program Directors, 1990. That predates any horizontal drilling of any shale anywhere. And it's the least restrictive in terms. And then in 2013, they rewrote it even weaker. So our legislatures passed a bill that was probably 2 steps up from saying that the earth is flat in their definition. They made up a definition that does not meet scientific muster. If you look at what US EPA says, the National Academy of Science, and ANSI, which is one of the engineering groups, they all add to that term naturally occurring potential for increased exposure. And what that says is, if it's a mile down here, it's naturally occurring and you probably don't have to worry about it. But from the moment the drill rig starts on the surface till the last barrel of brine and oil and gas come out of that well and it gets closed up, everything is technically enhanced. Because to get it, you need a lot of equipment. And most people don't have drilling rigs that cost umpteen $1 million sitting in their driveways. So it's technically enhanced. And why does that matter? To know how high the radiation is. Because there are cleanup standards and there are drinking water standards that oscillate around the radium. And the number is 5. 5 picocuries per gram is clean enough on a surface for a cleanup site. 5 picocuries per liter is safe for you to drink. Anything higher than that is classified as low-level radioactive waste. But Ohio, because they have said, oh, well, it's naturally occurring, we don't have to measure it, only checks drilling mud, if it's spent, maybe. Filter socks, if you can find them, maybe. And scale and pipes. And everything else gets a Hail Mary pass and doesn't have to be checked at all. So, we go back to this issue of, we know black shales are radioactive. That's why Oak Ridge is where it is. They got some of the early uranium for the Manhattan Project came out of black shales. We know that we have this thorium to radium-228 series and uranium-238 to 226 series that are problems. We know that the radiums and the uraniums are water soluble. This is important. Everything else, with the exception of radon gas, stays with the rock. But the radium is water soluble. It's also in the brines. And you get back to 5. Now, you'll hear people say, oh, it's not a problem. It's just like the granite on your countertop. Well, no, that's actually not true. USGS did this wonderful study and published it in 1997. And if you look at the bars, you'll notice that the high end of the wide part on granite rock is lower than the low end on black shales. Now, between 10 and 100 parts per million is the range for the Marcellus. We don't know what the Utica is because we've got very little data on it. If you'll notice, the fly ash from the coals is a whole lot higher than the coal. And that's because when you burn coal, the heavy metals and the radioactive metals stay with the ash. And it concentrates. And it was actually this problem of what were we doing with all of our boiler ash that got me back into taking environmental isotopic geochemistry, because we had it all over leaking landfills that were leaking into public water supplies. And we had radioactive wastes coming into our public water supplies that we had to deal with. So you hit 100 parts per million, you have a low-grade ore. You have a low-grade uranium ore. This is not something you want in your backyard. So, how do we know that what we're pulling out of the ground is radioactive? Well, we know the black shales are radioactive, but it has to do with the relationship between the total organic carbon and the gas and the radioactivity. We know the higher the total organic carbon, the more radioactive it's going to be. But we also know that if you want oil and gas, you have to find the areas to do your laterals that's got the highest total organic carbon. So what they do is they run a wire line with a gamma logger down, and they look for the absolutely hottest part of the shale they can find. And that's where they put their laterals. So now you're not drilling out average. You're drilling out the absolute hottest, because that's where they're going to get the most production. This is decades and decades and decades we've known this. And here's where we get back into chemistry. So this is, bear with me, this is Chemistry 101. This may be way, way, way too simple for half of you and just about right for everybody else. Here's why we worry about it. Here's calcium. Calcium is in your bones. Here's radium. It's water soluble. If you drink water with radium in it, it replaces the calcium in your bones. And it replaces the calcium in the fish and the mussels and the raccoons that drank out of the water, and the deer and everything else that drank out of that water. And that's why the number 5 is so critical. Because if you get radium in your bones, it will then continue to degrade all the way down to lead. We also have a problem with lead-210, which is somewhat water soluble and will also go into your bones. So we're dealing with some stuff that, if it gets loose into the environment, can be a real, honest-to-God health threat. Now, radioactivity exposures can give you cancer. It can also change your DNA, because that's how we get mutations. If you're drinking brine, you're going to die from the salts long before you die from the radium. If you're drinking really tainted water, first of all, you wouldn't want to drink it, but if you did, there are other things that will kill you much, much faster than the radium. But if you're only getting some of the radium, but it's enough, then it can cause problems long term. So we talk about rock cuttings, which in Ohio is considered norm and clean. And it's like they magically appear on the earth, but they don't magically appear on the earth. They come up because we float them up, and we float them up in drilling muds. And so when they come up, they're covered with drilling muds. And even the state of Ohio admits that drilling muds are T-norms and radioactive. But they treat rock cutting like it's something benign, and they ignore the fact that they're completely coated with dry muds. And here it is coming up. You see the water coming out? Well, that's muds coming out. And so once it's dry, it's completely encapsulated in drilling muds. So you have now not only the radioactivity of the black shale itself, you also have the radioactivity of the muds. And nowhere could we find any definition where they're going to go in and wash them off. And if they did, what would they do with the water anyway? So if you get a chance, and we can load this, these are really nice little short videos that show how they bring the drilling up and bring the stuff out. We have a little bit of data on the Utica, not very much. Data that was put together by the Ohio Department of Health in 2012, and we'll talk about how they did it in a little bit. But 5 is our number, okay? So here's a mud. You want the 228 and the 226, and together they're supposed to be less than 5. Okay. Here we're 224, we're 173. Here we're 600. Okay, add 650, add 225. You're a whole lot higher than 5. Okay? Here's our production water. Production water, maybe brine, maybe flowback, maybe we're not quite sure what. But production water. 1,070. Another 950. 838. Okay? So we're 2,000. Okay? 2,000 is not 5. Here's a vertical mud. We don't know where it is. We just know it's a vertical mud. 159 and 566. Whole lot more than 5. A horizontal mud. 264 and 601 or 578. Again, a whole lot more than 5. And another mud. 206 and roughly 650. Again, a whole lot more than 5. So the little tiny bit of data that we finally got, and it took a year and a half to get this from the Department of Health, by the way, and a FOIA, a Freedom of Information Act. None of this looks like 5. But according to the state of Ohio, only the mud and the filter cakes and the scale has to even be tested. And the next question is, how do they test it? You know, one of the things you always get into when you run any kind of a test or any kind of a model is you need to understand the underlying processes that that model or that test is going to do. Well, the EPAs and the Department of Environmental Protections across the United States did not have a good method because US EPA did not have an approved method. But they did know about the Safe Drinking Water Act, finished water 900 methods. And what do those, well, we'll talk about what they assume. But everybody knew what the 900 methods were. It was the only one that most of the EPAs and DEPs even had heard of. Labs were certified for this technique. They knew what it was. It was a wet lab program. You precipitate out the total dissolved solids and you count them for 2 hours. You had required lab testing methodology already approved. For shale wastes, they're absolutely the wrong test. And how do we know that? Well, because there's this wonderful paper that came out in July that made my life all of a sudden work. US EPA decided that they were going to study all of the methods to do laboratory testing to see what radium numbers they were getting and which ones worked. And what they talk about with the 900 method is it involves evaporating the sample to a thin layer of solid residue in a stainless steel platchet, okay, a little plant. And then they count it for 2 hours. The critical point is thin layer. Thin layer. It's wet chemistry. You're precipitating out the solids. You're evaporating the water out of what's there. And this thin layer gets counted for 2 hours. Well, shale wastes are not finished drinking water. A finished drinking water is clean, clear, and ready to drink. This is finished drinking water. Shale wastes are ground rock cuttings, sludges, slurries, filter socks, flowback, brine, scale, and landfill leachate. They're full of solids, total suspended solids, total dissolved solids, heavy metals, and salt. And there is nothing clean, clear, or ready to drink about them. You know, how do you precipitate out rock cuttings? And so in 2014, this last July, US EPA put out this document where they rank the lab tests against the Department of Energy gold standard classification for radium. And this is now available online. And this made my life so much easier. And the laboratory work was done at the University of Iowa in their state hygienic lab, which is their health department. And the secret of what went wrong comes out in the non-rad chemistry. And it's this number right here. This is out of a 55-gallon barrel of flowback and produced water out of the Marcellus. And they got 278,000 milligrams per liter of total solids. 278,000 was a disaster. Because when they went to run the 900 level drinking water, they got such a dump of precipitate, they didn't know what to do with it. So they modified, and they modified, and they cut with distilled water, and they cut with distilled water, and they put in less flocculation and all kinds of stuff, because supposedly all of these public labs out there, that these private labs that people are sending stuff to, is modifying the 900 levels. But nobody will tell you how they're modifying it, and I think it's because nobody really knows. I've asked Ohio EPA 3 times for the protocol for modification, and I've gotten dead silence, which means they don't know how they modify it. But Iowa said they couldn't. And so here's what they got. Even with modifying as much as they possibly could, when they ran the 900 method against the method that the Department of Energy tells you to use, they got less than 1% of what there was really there. Less than 1%. So does that mean you can believe the data that people give you that have been run from labs with the 900 methods? No, you can't. This is another precipitate on manganese oxide. Not much better. This is a filter disc methodology. This is run on radon, and then this is the full program that is approved by the Department of Energy, which is put it in a jar, throw in some agar to hold it, put it in a jar, seal it up, hold it for 21 days, and count it for 16 hours. That's the test you need. And what they found, and this is straight out of a publication, there are 2 publications that came out. This is straight out of American Chemical Society. It says, precipitation and concentration is not effective. So when people give you chemistry, look and see how they ran it. Because everybody's running 900 method, which means none of the data is any good. So, this is the 900 series up here. The MnO2 is a pre-concentration of radium on MnO2. The rad disc is something that's made by 3M. It's a filter. It's a little bit better, but still not good. The RAD7 is a radon emission measurement. It's a mineral oil extraction and liquid scintillation counter. And then the HPGE, which is gamma spectroscopy, 21-day hold and 16-hour count. Now remember, the 900 was a drop and a 2-hour count. This says hold it for 21 days and count it for 16 hours. Why? Well, the reason is because we're looking for the things in red. We're looking for the uranium and the radium. But radium is not a gamma emitter. It's either alpha or beta. So you can't measure, well, there's sort of a way, but by and large, you can't measure real-time gamma and know anything about your radium levels. So what you gotta do is you gotta wait until you get to the great-granddaughters and the great-great-granddaughters, and you come all the way down here, and what you're doing is you're measuring the lead and the bismuth because they've come into equilibrium. That's what the data from Ohio Department of Health was. It's the 21-day count. So we know that data is good. It's the only data for the whole state of Ohio that I've seen that I know is good. But that data is good. So we're waiting for this to come into equilibrium. And how long does it take? Well, here's the curve, the ingrowth curve for radium to radon. And at 21 days, you are almost at 100%. If you hold it for 3 days, oh, you're getting close to 50%. Now, if the number is 5, and you hold it for 3 days, and you get 3 plus or minus 6, is it above 5 or is it below 5? You don't know. If you hold it for 3 days and you get 927, well, then it doesn't really matter because you know you're over 5. But if you're worried about 5 and you're dealing with stuff that might actually be, 10 or 15 or 20 or 30, then it matters how long you hold it and how you run it. Now, why do we have to do it in the lab? Well, our research has shown us that trying to do this with something in the field just doesn't work. If you go in with a Geiger counter that's counting alpha or counting gamma or maybe a beta, all it's going to tell you is that you're getting a whole number of counts. But it doesn't tell you what you're getting counts of. And if you ever get up to isotopic geochemistry, you'll discover that virtually every element has got a radioactive isotope, or 2 or 3 or 4. So just knowing you've got gamma doesn't tell you that you've got 923 milligrams per liter or milligrams per gram of picrocuries per gram of radium. It doesn't tell you that at all. So that doesn't work. You'll find that Pennsylvania uses vertical poles that they drive through. Their goal is set for 10 millirems an hour, and then an alarm is supposed to go off. Well, if you talk to Ludlam, which is the company that manufactures the ones in Pennsylvania, they'll tell you they don't work for drilling wastes. They don't work for drilling wastes because they were put in for hospital wastes. And they work really good for, various kinds of irradiated hospital wastes. But they're lousy for this. And if you really could get one to go off at 10 millirems, and Pennsylvania is finding it's more like 30 or 50 millirems, then what's really inside the truck going in may be more like 200 picocuries per gram. So those don't work. So we've got handhelds that don't work. We have drive-throughs that don't work. There is something that may actually work pretty well. That isn't instantaneous, but it's not 21 days. There is a piece of equipment put out by Canberra. It's called an in-situ object counting system that consists of this wheeled gadget and a computer program. It's been used by the Department of Defense and Department of Energy for a long time. It scans whatever it is that you've got your container of materials are. And then working through a computer program, it backs out and gives you a relatively good estimate of what you've got. It's a 15-minute to a half-hour at least scan. It's not something that's going to work at a landfill with trucks coming through. But it's been around for a long time. They use it in the nuclear power industry. And so there's a link for it. And so, I'm not going to tell you there's nothing short of 21 days. There is. Will it give you what you need? Maybe. Can you do it instantaneously with trucks coming through? No. Which gets us back to this whole idea of how do we know what's coming into our landfills, which, of course, we don't have to test for anyway in Ohio, so it doesn't really matter, right? Okay. We're landfilling this waste, all the solids, all the filter cakes, all the everythings are going into landfills. And in 2013, they said we only have to test for the things they're calling T-norm. And if it's more than 5 picocuries per gram, which how you're going to figure that out, nobody knows, you can downblend it with stuff. You can mix it with dirt. You're not required to chemically bind that radium. So you mix it with dirt or sawdust or auto fluff or whatever, and you stick it on a pile, and it rains. And guess what happens? All the rock cuttings stay in the pile. And, it's all full of, you got a little bit of radioactive stuff and a lot of stuff that isn't, and now you got a lot of stuff that's radioactive. The radium goes. The radium moves out. It leaches out. And furthermore, that pile makes more radium tomorrow, and next week, and next year, and next decade. And it makes it over and over and over again until the sun burns out. And that's one of the big problems. So, most solids and semi-solids, norm, no testing, whatever. We even took away the requirements of saying how much we were sending to where. So we can't even go and back calculate to figure out how radioactive that particular landfill may be, because that was removed as well by our infinitely wise House and Senate and governor. And now on top of that, they are assigning beneficial uses to this material, which means you don't even have to put it in landfill. You can use it for a landfill cap, you could surface repair, you can even put it in the final cap. You could spread it in your backyard because it's a beneficial use. It's radioactive waste. It's higher than 5. Are our landfills low-level radioactive waste landfills? No. How do I know that? Because in 1992, Truman Bennett and I sat down. He was on the Blue Ribbon Commission to figure out where we would put one. And we figured out where in Ohio we would like to put it. And I can tell you there isn't a single landfill on that picture I just showed you that hit the places that we chose. So I know it doesn't meet the requirements because I know what the requirements are. There's a wonderful set of fact sheets on the web extension that goes into discussing what it takes to be a low-level radioactive waste landfill. And that is not what Ohio's landfills are. If it's liquid, it goes to a class 2 injection well. Now, maybe that's a brand new well. Maybe that is an old gas and oil well out on your grandfather's back 40 that somebody drilled in 1943 that isn't making anything anymore, but it's a hole in the ground, and they want to convert it, and they can. So our rules and requirements for injection wells are pretty iffy. And the other thing that's interesting is that if you ever became an injection well, and the oldest one is about 1960, you're grandfathered in, and you can be an injection well forever. And even as things change and requirements change, those old ones keep working, and they don't get changed because they were grandfathered. So there is a clause as of 2012 that looks at the issue of seismic rules. And we do have some cases. And that was because of the case here in Youngstown. Okay. How about beneficial use? What does this mean? Well, some people were saying, well, we can compost it. Okay, we can. We can compost it and we can treat the hydrocarbons. But composting doesn't treat heavy and radioactive materials. So if you take these mixed rock cuttings and the drilling muds and everything else you've got, and you put it on a compost pad, and you treat it with microbes, and it rains, the radium's going to move out. And you may very well contaminate your compost pad to the point you can't use it for anything else. And nobody knows what's going to happen to the microbes when they get introduced to all this radiation. My research partner, Dr. Ann Christie, is the biological engineer in our department, and she's very fond of microbes, and she doesn't like the idea of putting them with this. Her expertise is composting and landfills and wastewater treatment plants and those kinds of things. So Ann says, I'm not sure this is a good idea. So if Ann says this is not a good idea, Julie says it's not a good idea. Well, what else can you do with it? Well, you can dump it down the storm drain, which is what dear Mr. Lupo did here, to the tune of about 1 million gallons at least, maybe more. And he went to jail, which is nice, or he's going to jail. You can use it for de-icing on winter roads. That's still legal in much of Ohio. And how you're going to know whether that brine came out of a shale well or it came out of an old Clinton or Berea or Oriskany or whatever, I don't know, unless you do the chemistry to look at the signatures. And if you don't want to pay for salt this winter and you need to de-ice your roads and you're a township and you're poor, and somebody comes up and says, I'll make you a deal, how hard are you going to look at the chemistry of what's in it? So this is another big concern. What are other states doing? Well, Michigan is monofilling the solids, and they're using a 50 picocurie per gram liter, or per gram limit. They're also using the stationary hoops. They're not sure that they're getting what they think they're getting. So they're in the middle of a big review right now. Pennsylvania is testing everything. It's 10 to 15 or 15 to 20 picocuries per gram, 10 millirems per hour. And they're putting it into monofills, the solids, in select landfills. They're burying it very deep. But they now know that their actual alarms are triggering at a much higher number, and they are finishing up a brand new 1-year study to find out how hot the stuff is that they've got. West Virginia wasn't testing anything. They were just putting everything into their landfills and testing the leachate twice a month forever. But now they're under new emergency rules that we just commented on. They're calling for monofills, and they're basically considering them low-level radioactive waste landfills. That's the solids and the semi-solids. Almost all of the liquids that aren't recycled all come here to Ohio. And we're getting lots of cuttings, too. And if the bells and whistles go off in Pennsylvania or West Virginia and they can't take it there, then it's supposed to go on a truck and head west, but there's nothing to keep it from stopping in Ohio. And there's no way of knowing how much we're getting that's over the limit from the other states. Now, we've got West Virginia data. And this is really exciting. We've got West Virginia data for 3 years now for the Meadowfill, Landfill, Monticello, and Bridgeport, West Virginia. And we've got 3 years for the Wetzel County landfill in Wetzel County on the Ohio River. And they're not looking at just radioactive. They're looking at 43 different parameters. And this last summer, Rachel Warren, who is from Youngstown, whose dad taught here in the business school, who's one of our students, put together an access database for us for the data out of Meadowfill and Wetzel County. And they're using the 900 methods, okay? So we know these numbers are wrong. We know they're low. But we're still getting alphas as high as 1,300, gross betas as high as 2,000, radium-226 as high as 23, radium-228 as high as 42. Add those up, they're a whole lot more than 5. And the one that's absolutely got me really wondering is the strontium-90. West Virginia looks for strontium-90. Now, strontium-90 is man-made. Strontium-90 can only be there if you have man-made radioactive material. One possibility, the test is wrong, and we may never see this again. 2 other possibilities. Halliburton has a patent to use spent uranium as the metal for the cartridges to shoot the casing for the fracking. We do not know it's been used in this region, but they have a patent for it. And why? Because uranium is a really tough metal. It's really hard. They use it for bullets to pierce armored vehicles. Okay? Spent uranium will give you strontium-90. Another possibility. There have been allegations, and I prove this? No, I have heard there have been allegations that man-made rads are being mixed in with these waste streams because nobody's going to check and a little bit can slip in. We certainly have case after case after case after case of old landfills in Ohio with man-made rads in them. Probably 10% of the old landfills are radioactive with man-made rads. So, could that be the case? Yes, it could. So I'm watching that strontium-90 number to see if it ever shows up again. So what did we learn from this West Virginia data? Well, it's the wrong tests. They're using the 900 method, so it's going to be too low. The count time, again, is way too short. You saw that high number after the plus or minus. It's only 2 hours. It's not 16. We don't know how long they're holding it. They're holding them different levels of time, but it doesn't really matter. We have unknown weather conditions and sampling locations. We have unknown volumes of leachate being generated. But we still have radiological numbers that are above 5. Are they 10% of what they should be? Are they 20%? Are they 5%? I don't know. But they're above 5, and they're not the right numbers. And we know that the Marcellus waste of all types are coming into Ohio from Pennsylvania and West Virginia. And so therefore we know, even though Ohio is not testing for this stuff, we know that Ohio's landfills are becoming radioactive. We know that. And we know they are becoming, in effect, low-level radioactive reactors. And that's what we're doing with our landfills. Now, Here's some data that Rachel put together for us. And this is 3 years worth of radium-226, 228, and the strontium number. This is from Meadowfill. And here's the number that's going to make the difference for us. That's our total dissolved solids. We never get below about 2,000. We get up close to 14,000, okay? That's not 278,000, but it's also not this. So we know that these numbers are too low. So when I found the paper that looked at the problem with the total solids, I said, Rachel, run me some graphs. Put the radium against total dissolved solids, and you'll notice that she actually has swapped the labels. The bottom should be the radiums, and the top sides should be the total dissolved solids. And I said, put them together, let me see. So here's what she got. So, question to the class. Do we see a relationship between radium measurements using the 900 method and total dissolved solid levels in the Meadowfill data? Can we use the ratios to predict more valid levels of radium from the 900 methods data? What do you think? I looked at it and it looked like a scatter shot to me. I'm not sure it's going to be possible to back out what a real number should be from the data that we've got. But at least it tells us it's there, and it tells us what we have to do if we want to get a real number. So in a couple of weeks, I'm going down to meet with the West Virginia Department of Environmental Protection and have this discussion about the fact that, we've got all this data, but it isn't any good, and let's talk about what we need to do to make it better. Will they listen? Probably a lot better than if I had this conversation at Ohio EPA. And one of the reasons is that I'm going to have one or two nephews in that room. So that may help, because they know that Aunt Julie won't lie to them. But are we going to get them to run the right samples? I hope so, because I hope they're going to understand that they're wasting their money by running the wrong ones. Now, if you use Michigan's number, if you use Michigan's number of 50, and you wanted this stuff to hang around long enough so it would be safe for you to be there, get down to 5, not dilute, just half-lives. How long would that take you? Well, the half-life on radium-226 is like 1,600 years. So if you go from 50 to 25, 25 to 1250, 1250 to 625, and then down to 5, you're at 3+ half-lives. What was going on 5,000 years ago? We were building the pyramids for the first time. So if you want to make that landfill safe from a radium standpoint, if you only have 50, that's how long you have to wait. If you want to make it safe for the uranium-238, the half-life on uranium-238 is more than 4.4 billion with a B years. It's almost as long as the Earth has been around. So if you want it to be safe for that, you got to wait till you're as far ahead as you are back to the Big Bang. That's a while. I don't think we're going to be here. And if you're going to worry about the thorium, now you're talking about something with a half-life that actually is older than the Big Bang. So now we're talking about a number we have no idea. But we can see 45 billion years, visible light. It's more than that. So now we're left with dilution. Now we're left with sacrifice zones and dilution. Because when that rock is in that landfill, it continues to decay. And it makes more radium and more radium and more radium. And if it doesn't end up in the leachate that goes to your wastewater treatment plant, which isn't prepared to deal with it, it goes into radon gas. And you know what happens when it's in radon gas? It goes out with the gas collection system, but it is a noble gas. And so it does not burn. But it's heavier than air, so it rolls down the hill. And it lays in the bottoms around the landfill until the wind carries it away. And it does that forever. So this is not a joke. This is real serious. And there are a number of us trying really hard to get people to pay attention to this. And other states are. There is a paper that we have been working on for a year and a half. And Jeffrey Dick is one of the co-authors. It is taking us forever. It is to look at everything we know about the Utica and Marcellus shales, the environmental and legal questions. It's the public health that has taken us so long. We're finally getting public health studies. The socioeconomic considerations have been hard to get handles on. Jobs are not there that people said they were going to be there. There are 11 authors, 5 universities, private sector. We've got scientists, we've got engineers, we've got public health people, we've got economists. We've got a real cross-section of people working on it. I used to say, oh, it'll be next season. I don't know when it's going to get done. But at least my part is getting to be that I can now write it because I've got the data I need. We will publish it in the Ohio Journal of Science. It will be online. We will put in the back appendix after appendix after appendix of all the information that's available. It will be publicly accessible. It is straight peer-reviewed science, okay, and law. It's not anybody's spin. It's what it is. And so with that, there's our contacts, and we're getting pretty close to being out of time. Questions?
Please repeat the question so we get it, good audio. So just repeat the questions after someone asks.
Which questions? Okay.
Well, I'll go first.
Okay.
So this Canberra in situ object counting system, is that what Austin Masters is proposing for this place in Youngstown?
Yes, it is. The question is the Canberra ISOSC or whatever it's called, is that what Austin Masters is proposing? And the answer is yes. I talked to the radiological engineer who works for them, and he comes from DOD experience. He's had years and years of experience with using this piece of equipment. And he thought it would be a good way for the oil and gas industry to find out what they really had in their materials, because he's extremely concerned about the idea of the landfills. There's a new landfill being proposed or an expansion in Columbiana County that's going to take cuttings. And he's very, very concerned about just bringing in stuff that nobody knows is what's in it. It will work. It's not quick. It's not something you can simply drive a truck by and wave and have it work. Will it be absolutely right for 5? I don't know. I've read the material that was submitted, and they said 5 plus background of 2 plus or minus up to 11.99 they thought they could get us. Now, 11.99 is a whole lot better than 250, okay? It's still higher than what we're requiring, but it's a whole lot better than 250. So if it really pegs out, you've got a big problem. It's certainly better than no testing. Will it get you exactly the numbers you want? I am not that familiar with it, but I have a mentor who has been teaching me geochemistry from Department of Energy for the last 3 years as fast as he can. And he says, yeah, Julie, it'll work. We've been using it into the industry for a long time. It'll work. But it's not super quick, and it won't be cheap. And when you don't have to test at all, why would you use it? Okay. Yes.
Follow up on that. So my concern is a false negative. and the company had said they were going to just do it in a matter of minutes. But you're saying it's at least 30 minutes.
The numbers how quick does it go? All right. I'm reading the website, and they're talking 15 minutes, so you figure you got to have setup time and all of that. They're talking 15, 16 minutes plus setup time and tear down time and all that. So I'm thinking you're looking at a half hour roughly. I mean, the reason that I'm saying that is because it's not a piece of equipment you would have by the side of the haul road coming into a landfill. And that's the critical point. When you're driving the trucks through, they just come and they come and they come. And how you're going to screen every single truck. I've worked on lots of landfills, and they just come and they come and they come, and you don't know what's in those trucks. So it's not quick.
With all the data, just speaking from chemistry perspective, why is there such resistance to listen to?
Why is there a resistance to listen? You want my real opinion?
Yes.
My real opinion is that there's a lot of money being thrown around. And there are a lot of campaign contributions being made. I can tell you Linda Aller from my office went down and gave part of this presentation to the House when they were talking about this in the budget bill and explained to them why their definition would not work, and they weakened it. So it isn't a question of whether someone qualified. At the time she did it, she was chair of the Ohio Board of Registered Sanitarians for the state of Ohio. There's no question about whether we were qualified and whether we knew what we were talking about there. But they didn't listen. So you have to speculate, why did not they listen? Yep, maybe they just didn't listen. Maybe they believe the earth is flat. I don't know.
Is there anyone in the political ranks, I guess, with the chemistry, just a basic chemistry background, that would have some sort of idea as to why you should be paying attention to this, why you should care?
Is there anybody in the House or Senate or in the high-level government with a basic chemistry background? I honestly cannot answer you that. I can tell you that Michigan, Pennsylvania, and West Virginia are scrambling like crazy and doing their homework, okay? And when I called West Virginia and asked them how come they were testing twice a month forever, they said, Julie, we're a year ahead of you. We got it a year before you did. We had a year more to think about it. So, if you have a government that allows for scientific inquiry, then I think you have a support. If you have a government that is not interested in scientific inquiry, then you don't. And right now things are worse than I've ever seen them in my working life. And I'm honest about that. Okay? I'm not against oil and gas drilling. I'm just against stupid, and I want them to take care of the stuff that they're doing, and I want them to take care of it properly. And I want to know how radioactive that landfill is, because maybe it's not that bad, and maybe we can dilute it. But I need numbers. I don't want to just, oh yeah, everything will be fine, because I don't know that. Yes. Yeah, which doesn't do any good and doesn't measure water anyway. No, so that was absolutely a waste of time. Patriot's methodology of testing is completely invalid. We've known that for a long time. Now, what was your other question? Well, the problem with the landfills is it doesn't just stay in the landfills, because the radium is mobile and it moves with the leachate. It rains on the landfills. All the caps leak. We know they leak. And the leachate goes to a wastewater treatment plant. And the wastewater treatment plant is not designed to take out the heavy and radioactive metals. That isn't what they do. Meanwhile, the people that are there don't know it's coming through and don't know if it's high enough that it's going to infect them. Don't know the impact of the workers on the landfills. Who am I worried about? I'm worried about the workers on the landfills who are being exposed to they don't know what. I'm worried about the oil and gas industry people who are being exposed to they don't know what, but at least they work for the oil and gas industries. Workers on the landfill don't work for the oil and gas industries. The public people that work in a wastewater treatment plant don't work for the oil and gas industries, and they're potentially being exposed. What does that exposure do to them? How high is it? We don't know. We do know that the numbers that we're seeing out of West Virginia and the salts that are coming out of the Wetzel County site, that leachate is going straight into a packaged treatment plant and then being dumped straight into the Ohio River. There is no dilution in that packaged treatment plant. All it's getting is leachate. Ann is concerned that the salts are so high that they'll pickle the microbes and kill the plant. So this isn't even a question of what the radium is. This is a question of how high are the salts and can you dilute it enough? Now, if you have a landfill going into all the wastewater from a huge city, yeah, you can probably dilute. But the other thing in West Virginia is while they're sending the leachate to wastewater treatment plants, they didn't add any new parameters to the NPDES permit, which is the permit you have for what comes out of the end of the pipe. So nobody's testing to see what's coming out of the pipe to see if they've got a problem. There are a lot of holes in West Virginia's program, and they're scrambling to plug them. But at least they're scrambling to plug them. Okay? This is happening. Drilling's going on. We got to deal with it. It isn't going away. So we better figure out what we've got, and we got to figure out what we're going to do with it. And it is up to us, the scientists and the engineers in this state, to handle this mess, because we've got it. Anything else? Now that I've thoroughly bummed you out. And I'm going to die and retire, so. Right. It was used originally by the Department of Energy and the Department of Defense. It was used for cleaning up old bomb-making sites like Piketon and Mounds in Miamisburg. And it was used for working at nuclear power plants to make sure that nothing was leaking, or if it was leaking, to have an idea what was leaking. Like when Davis Bessie that was eating a hole through the cement. Yeah, that was eating a hole through the cement cap and almost came loose. So these are standards for cleanups. These are used at Hanford. These are used at Utica, Kentucky, which is an old rad waste problem. So, and the way they found out that Paducah, Kentucky's landfill was leaking is somebody flew over it with doing a ultraviolet and infrared photography, and the trees fluoresced the wrong color, and that's how they found out it was leaking. So, every landfill leaks. They all leak, folks. We can't make them so they don't leak. So this is going to leak, and it's going to fail. And they're only funded for 30 years post-closure. And this stuff is not going to be okay in 30 years. So who's going to pay the cleanup? There's no money in the post-closure fund after 30 years. It's going to fall to the local health departments, the local county commissioners. That's who's going to have to pay for it. Where are they going to get the money? They didn't get it from the oil and gas industry. It's about the dollars and cents. Okay? I'm sorry to have ruined your day.